Right. Grade 11s. Yesterday we spoke about electron current versus conventional current. Without looking at your notes, who could tell me what is the difference between electron current and conventional? Electron current flows from negative to positive, obviously conventional. From positive to negative. Something else? Okay, electron current you indicate with an arrow with an E negative next to it, whereas conventional current is just an arrow, no E negative next to it. Okay? What else is the difference? In electron current, the electrons are flowing, and in conventional current? Well, I wouldn't say protons are flowing, but we imagine that positives are flowing. Okay, we now know that protons can't, so we'd imagine that positives are flowing. Dylan? Right, electron current is what happens in reality in 90% of times. If we look at lights like these fluorescent tubes, there you do have electrons moving in one direction and positives moving in the other direction. So you sometimes can get positives moving. But in a normal copper wire situation, it's electrons that move. So electrons are what happens 99% of the time. Yes. Okay, so electron current is the real thing. Conventional current is almost an imaginary situation. But it doesn't matter which one you work with. It has the same effect. Let me give you an example of what I mean by that. Let's say that Chris here he owes some loan shark, because he's been borrowing money to pay off his debts. He owes a loan shark 5,000 rand. Well, let's keep it simple. He owes a loan shark here at school. He's been borrowing money to buy stuff at the tuck shop. He owes 100 rand. Okay? And I know that Chris is taking strain, because this loan shark is a tough guy. He's going to start breaking Christopher's knees soon, or his knuckles, or things like that. So I just quietly, I'm going to help him out. How can I help him out? There are two ways I can do it. Besides going to go sort out the loan shark. Well, I can go to Chris and say, here's 100 rand. You agree? So that is positive money that flew from me to him. What was the direction of movement? Me to him. Real money, something positive. Or what could I do? What could I say to him? What can he give me? Give me the account. Now the account is a negative thing, isn't it? Which way is the account flying? From him to me, the other direction. Either way, he gives me the debt. It's now my problem. I'll sort it out. He's okay. He's back owing no one anything. Understand? So you can either send negative one way, or you can send positive the other way. It has the same overall effect in the end. And that's what the same outcome with electricity. Whether you imagine electrons flowing that way or positives flowing that way, it has the same overall effect in the end. Now, can anyone just tell me, let's start off with real basics. What instrument do we use to measure electricity current with? A what? Ammeter or ammeter? Okay, first of all, what is current? What's the difference in current and voltage? We spoke about this the other day. Never got around to it, I know. We spoke about it. Okay, who can tell me what current is? Flow of what? Electrons. What is voltage then? How strong the current is. Okay, what is power? How strong, how much, the flow. Do you have a clue? Do you have any clue? Okay, let's compare it to a car. Your current strength is your speed. That's how fast the car's moving. That's all it is. Your current strength is your speed of your car. So in electricity terms, what is your current strength? Your speed of the electricity, the electrons, or the charge. Okay? Are they moving slowly, or are they moving fast? That's your current. Which is what current is in a river. The current's strong, or the current's weak. Right, so no difference there. What is your voltage? Is a car's speed the same as its power? Give me an example of a powerful car that's got a low speed, that's traveling at a low speed. A dump truck, okay, it's really powerful, but it travels slowly, but it can carry a heavy load. I could have a Lamborghini traveling at 20 kilometers per hour. You agree? It's got power, but it's not using it to give it high speed. So voltage is the power behind it. How much energy there is to push that car if you unleash that energy. You're not always going to unleash that energy. What would your resistance be equivalent to with a car? Your brakes. Okay. So if you apply brakes just a little bit, it's a low resistance. The car can still go quite fast. If you apply brakes with a lot of brake, your car is going to stop or slow down. You would agree? Now, what would be a good combination to get a high speed? What would be your combination between the power of the engine and the brakes? If you want a car to be going fast, do you want to be using a lot of brakes? No. Do you want a little bit of power? So you want a lot of power, no brakes or very little brakes, then that car is going to move. It's the same with a current. So if you want a fast current, what must you do with the voltage? High energy, lots of batteries, okay? And what must you do with your resistance? And that's electricity. Really, electricity boils down to, okay, so I will give you the notes. Current electricity boils down to three things. Everything is I. What does I represent? The current strength, the speed. This is the critical thing in electricity. And why, you may ask? Well, if you want your volume of your sound system to be turned up, what must you make sure happens? The current must be stronger. If you want your earphones to give you a louder volume, you get a stronger current to your earphones and you'll hear louder music. If you want to turn it down, you slow the current down and you get quieter music. So current affects almost everything. If you want your electric stove at home to be hotter, what do you do with the current? You jack the current up, the plate gets hotter. If the food's burning and you want to cool it down, you bring the current down, the plate gets cooler. Okay? So current determines sound. Current determines the heat of a hot plate. If you've got lights that you want to dim, the lights, how do you make them go dimmer? What do you do to the current? Slow the current down and your lights go dimmer. If you want your lights bright, you turn it up, your lights go brighter. Current affects anything to do with electricity. It all comes back to current. Now, there are two factors that impact on current. What are they? The voltage is the one. Okay, and what's the other one? The resistance is the other. So, what really matters is the current. What affects the current? Two things, voltage and resistance. How does the voltage affect the current? What would happen if I increased the voltage? What would happen to the current? What did we say the voltage was equivalent to? The power of a car, the engine strength of the car. Okay, so let's call this the engine. Happy with that? We don't have to use the full strength all the time. We can keep our foot off the petrol and use only half the engine strength. but the voltage is the engine strength. What did we say the resistance was? The brakes. Okay, and what did we say the current was? The speed. If we were to compare electricity to a car. So right, you want a high speed, what do you do to your engine? Get maximum engine strength, lots of petrol. You want to slow it down, what can you do with your voltage? Reduce your voltage. What can you do with your brakes? Increase your brakes. You agree? So let's make a formula out of these three things that tell us how they work. So that if I increase this, this gets bigger. If I increase this, this gets smaller. What would that formula look like? Give me a formula that when this gets bigger, this also gets bigger. When this gets bigger, this gets smaller. I, the current strength, the speed of the electricity, equals the voltage divided by the resistance. You've all seen that formula before. Okay? That is a critical, probably the most important electricity formula you're ever going to get. You're going to use it over and over and over. Right, so I equals V over R. So really, in the end, if we want to understand current, we need to first understand voltage and resistance. If we understand these two, then we can control that. Who panics about electricity and doesn't like it? Who else feels that this is the one section of work that, it's not. So you're all okay on it. You're happy with it? You happy? Okay, we'll find a couple of circuit diagrams for you just to keep you on your toes. Okay, electricity grade 11s is the one section you should all be getting full marks for at the end of this year. Okay, at the end of this year I want you to get full marks for electricity. Have you dealt with internal resistance yet? Okay, we'll deal with that. Right, so there's your formula. Let's have a look at, okay, what did we say was the thing that measured the speed of the current? What measures the speed of a car? Your speedometer. In an electric circuit, we use the ammeter. Notice it's not an amp meter, it's an ammeter. Okay? And the symbol for an ammeter is an A in a circle. Right. Now an ammeter is normally connected into the circuit. Let's say you've got the battery. Let's say you've got a resistor. And let's say you've got a switch over here that's closed at the moment. Where would you put the ammeter? Before the resistor. Okay. Why do you say that? So if I had to put an ammeter there, let's call that ammeter number 1, and I had to put another ammeter there, ammeter number 2. Which one would have the higher reading? A1 would all have the higher reading. All agree with that. Where to? You sure? You? Who says that one would have the higher reading? That maybe the electricity is slowed down over here, now it can go fast again. So, okay, who says that's the higher reading? Hands up. Okay, who says that one's the higher reading? Hands up. Who says they both got the same reading? No. Jock, you do. I'm afraid, Jock, you're the only one who's right. Bunch of sheep, you just follow each other. Right, let's try and see how it works. Let's take a garden hose. Okay, let's take a garden hose. Here's your tap. Okay, that's coming from the dam, okay? You connect the hose to the tap. Right, there's your hose. And the water's flowing out pretty fast. Let's say it's flowing out at 5 liters per minute. Okay, you all agree? So you've opened that tap pretty fast. Water's flowing through that pipe at 5 liters per minute. Can anyone tell me at what rate is the water leaving the dam? 5 liters per minute. Do you agree? Let's say no one else in the country is using water, just you. You've opened your tap, so water's flowing out of that dam at 5 liters per minute. It's flowing through the pipe at 5 liters per minute. It's flowing out of the pipe at 5 liters per minute. All happy with that? Okay. I now come and I squeeze the hose pipe so that I restrict it. Okay. What does that do to the water speed over here? Slows it down? No, it may make it. I squeeze it in the middle. So I don't squeeze it on the end. Squeeze it in the middle. What does it do? Slows it down. Maybe it changes to 2 liters per minute. Now this is after the resistance there. Okay? What happens before the resistance? What happens here to the water speed that's leaving the dam? You say it's still flowing out at 5. Because then that hose is just going to explode somewhere along the line. You agree? It slows everything down. So here you've got like a hose pipe. Not with water flowing through it, but with what flowing through it? Electrons, electricity, charge, whatever you want to call it. So these charged particles are flowing through it. We imagine they're what charged particles if they're flowing out of here? Little positives. We know that's a load of rubbish, but we imagine it because that's what they want us to do. Okay. We slow it down. It must slow down everywhere. It can't be flowing fast here and slow there, because then you're going to have an explosion of electrons. All understand? Electricity is simple, people. Okay, so we want to just have a look at it. Ammeters, this velocity before the resistor and after the resistor would be the same. So let's say this gave us a reading of, choose a number, 2 amperes. What would it be here? 2 amperes. Good. Okay. Right. How do I connect an ammeter? So I can connect it anywhere in the circuit. Yes. Okay. How have I connected it here? Series or parallel? Is that in series? What would have happened if I had to put an ammeter there? That's in parallel. What would have happened? Which way would the electricity flow? Would it go through the ammeter or would it go through the resistor? Okay, let's change the resistor. Let's not make it a resistor. Let's make it a lamp. Okay, I connect an ammeter over the lamp in parallel. What will happen? Will it go through the lamp or will it go through the ammeter? Through both. So if the electricity that's now arriving here, how many amps are arriving at this point here? 2 amps. How much goes through the ammeter and how much goes through the lamp? So you're saying 1 would go through there and 1 would go through there. So is this ammeter actually going to read 1 amp or 2 amps? How can it read the one that's going through there? It only reads what goes through it. No, it's not calibrated for it. And what's going to happen to your lamp? If it used to have 2 amps going through it, but as soon as you put the ammeter here, it only gets 1 amp. What's going to happen to your lamp? It's going to go dim. Does the lamp go dim because you put an ammeter in the circuit? Not quite. In fact, what will happen is this won't happen. You'll get no amps flowing through there. And the amount of current that flows through the rest of your circuit will spike way beyond 2 amps. Because what was keeping the current down to 2 amps before I put this ammeter in? Your resistor was your brakes. It was saying, here's this powerful engine that just wants this electricity to flow fast. And what if a car goes fast all the time? What happens to its energy in its petrol tank? It uses up its petrol and it can't go anymore. The same with the battery. If it goes flat out all the time, if it causes current to go flat out all the time, it uses up all its chemicals and it can't work anymore. Okay, so what keeps the battery in check? The brakes, the resistance. That resistance, either a resistor or a lamp, was controlling it and saying, well, between you pushing the current and me slowing the current down, it's going at 2. Okay? And between the two of us, we're controlling the current at 2. Now we put an ammeter which has got a 0 resistance over here. So it's got 0 ohms of resistance. The electricity gets to that point. The electricity is not stupid. It says, I can either take the difficult route through the lamp, got to work my backside off to get through the lamp, or I can take a nice easy route, no resistance. What do you think it's going to do? It's all going to go this way. So what's my resistance of my circuit? 0, because copper wire's got no resistance and ammeter's got no resistance. So let's say this was 12 volts, and let's say this was 6 ohms before. What was my current before? I equals V over R. What was 12? Or what was V? 12. What was resistance? 6 ohms. What was my current? 2 amps, as we saw. Okay. Now I take this out of it. I equals V over R. What is my voltage? 12. What's my new resistance now that I've taken my resistance out? 0 ohms. 12 divided by 0. Anything divided by 0 is infinite. You've got this massive current that flows, which flows for about a minute, and then your battery's dead. And on top of it, it didn't flow through your lamp. It flowed this way. So you don't even have light, and you flatten your battery. Who of you have done that with batteries before? Why is this battery not working? I must take it back to Pick and Pay. Okay? If we take a typical battery, there's your battery. These type of batteries with the terminals on the top. Okay, 9-volt battery. There we go. This battery's got plenty of energy in it. It just wants to push electricity fast. Okay? You take your copper wire and you're now playing around and you connect a copper wire there. How much resistance has that copper wire got? None. Electricity motors through there for a minute and you've got a dud battery after that. Then you take it back to Pick and Pay. Right? And it also gets hot because the current is flowing so fast. It's fun. Oh, best way to start a fire. Okay. Right, so people, electricity is really, really simple stuff. What's the most important part of electricity? Current. What are the two things and the only two things that affect current? Voltage is like the power of the engine, okay, and resistance is like the brakes. We look at a circuit, there's the power of the engine. All comes back to the battery. What controls the speed? The resistance, the brakes. So resistance can be a resistor, it can be a light, it can be a motor, it can be anything that uses electricity. That's your resistance. Okay, and between these two things, they determine the speed of the electricity, which is measured by an ammeter, which is never, ever connected in parallel, because that gives the electricity a bypass around the resistor, which gives you a 0 current flat battery. Okay, so ammeters are always connected in series. And ammeter's got a high resistance or a low resistance? Low resistance. Okay, why do you want them to have a low resistance? How would you like to go and connect a speedometer on your car and it slows your car down? Okay, yeah, you're traveling at 140 because you know there are no speed traps. Switch on the speedometer down to 80 because your speedometer slows the car down. Do you want that? Do you want an ammeter that's going to slow the current down? The current's got to flow through the ammeter because it's in series. It's got no choice. It can't go around it. It can't hop over it. It's got to go through it. You want an ammeter not to affect the current. You want it to give you the actual speed. You're traveling at 140 kilometers per hour, not when the speedometer is switched on, your car speed changes down to 80. Let's give you the real speed. Okay? So your ammeter has practically 0 resistance. A good ammeter is like 0.00001 ohms. You can never get 0 resistance entirely. Okay? A cheap ammeter like we use here, 0.2 ohms, that type of thing. Right. Any questions? Let's give you some notes. Who's absent? Sorry? Just made it. Who's keeping Giovanna's and Nikita's? Well, we're still missing Giovanna's notes. Will someone take Nikita's? Okay, then we only have to give notes to Giovanna, otherwise it becomes a nightmare. And the chances are Giovanna won't come back to school for her notes anyway. She's absent so often. Right. Get those notes pasted in or labeled. Not going to paste them in now, you can do that later. Okay, let's read through those notes. Page 6. The instrument for measuring current is the ammeter. If we go back to the previous notes that you had, you just flip back. We're talking about current flowing. What makes current flow? Am I right at the top of the page? The electric field in the circuit. Then we looked at conventional versus electron current. Right, now we turn over to page 6, the notes I've just given you. The instrument for measuring current is the ammeter. That's the symbol for the ammeter, a circle with an A in it. And the two lines that run out horizontally show that it is connected in series. If I'd drawn lines like that, drooping down, then it is in parallel. So if I show something in series, that is series. And if I show something in parallel, that is parallel. What would that be if it was in parallel? A voltmeter. Okay, right. It's always connected in series and it has a very low resistance, almost zero resistance. All happy with that? Another formula for current strength. Now I want you to turn back to page 1 on electrostatics. Right when we started electrostatics. Before that, there you are, page 1 of electrostatics. There, halfway down the page, you had a formula. Q equals I times T. So from that, you could have got a formula that I equals Q divided by delta T. Do you all agree? Okay, so that's one formula for current. We don't use that formula very often. This is the formula that we use a lot. Little tick there, 4 ticks there. Okay? Probably going to use this at least 10 times more than that formula. Where I stands for the current, always measured in amps. No. How do you abbreviate amps? Amperes. Okay. You either write it out as amperes or you write it out as capital A. But to say amps, not only will I give you naught, but I'll also kick your backside. Okay, the official abbreviation of amperes is A. Right? Charles d'Ampere or something like that. Right. Voltage is the V in volts. R is resistance in ohms. George Ohm. And someone Volta, an Italian scientist, Volta. Omega. I'm not too sure how old George decided, but yeah. Okay, right. Let's read on. Factors that affect current strength. We look at this. We said, what are the factors that affect current strength? Voltage and resistance. There they are, 1 and 2. Voltage, the higher the voltage, the stronger the current. In other words, if I double the voltage, I will double the current. You agree? And resistance, the greater the resistance, the weaker the current. They work just in the opposite way. So the greater the resistance, the lower the current. We can say that I is inversely proportional to the resistance. Let's have a quick look at those proportionality symbols. Let's take all of this off. How much time do we have? 5, 6, 7 minutes. There's our formula. You all agree? Right, let's take a situation, 2 situations, where we've got the same resistance. Choose me a resistance, please. A nice, easy number. Like 2. Thank you. Good. Choose me a voltage. 10. What's my current going to be? 5 amps. Right. Simple. We can all understand that. Choose me another situation where I've got the same resistance. I haven't changed the resistance. I only change one thing at a time. But change the current, the volts. No, nice number, nice. Should we make it 20? 20. Do you agree? Resistance has stayed the same. But what have I done to the voltage? I've doubled it. So what's going to happen to my current? The math tells you it's going to also come out to be double. So if I double the voltage, I'm going to double the, so that was times 2. This became times 2. Right, and what does that mean? That the current is directly proportional to the voltage. Okay, we're happy with that. That's what that means, directly proportional. And directly proportional means if I double the one, I double the other. Extremely important. Right, let's have a look at the other one. Let's choose another set of figures here. I equals V over R. Choose a nice V like 12 or 2. No, make it 3. Okay. What's my current going to be? 4 amps. Right. Now, what am I going to keep constant in the next one? Keep the voltage constant. So I still equals V over R. Voltage I'm keeping constant. It stays. Let's double resistance. 2 amps. So what did I do here? I times it by 2. What did I do here? Divided by 2. So we can say that I is, now what's the symbol for inversely proportional? 1 over, and I use the same proportional sign. 1 over R. So current is inversely proportional. These two things read together to R. Okay. So, and not indirectly. Yeah, I'll go and write indirectly. In inversely proportional. We all understanding what that's about? Been through it a number of times now. So far in your science career, you should have a good grasp of that. Okay, all happy. Now we're going to have a look at voltage in more detail. And that's what we're going to spend the next day doing. We've still got 5 minutes. So can we clear the board? Yes. Yes, I could. How would you answer it? 2 marks. So what would your answer be, Jock? As the resistance increases, so the current in the same proportion. If you double the one, the other one will halve. In other words, now that would be my 1 mark. So as the one increases, the other one decreases in the same proportion. However, or we can therefore say current is proportional to the resistance. That's what you'd be required to say. That will give you your 2 marks. Right. And we said our formula was I equals V over R. We will be doing a prac sometime about that. This whole thing, this formula, is actually known as Ohm's law. Did you deal with that in grade 10? Okay. There's a law, a wordy law that you're going to learn the words, but that's it in mathematical format. Right. Now, at school level, where do we get our voltage from most of the time? Batteries. Okay. So most of the time we're going to get our voltage from batteries. Now, what is a typical cell? Because we shouldn't talk about batteries. Battery is a collective noun. A what of sheep? A herd of sheep. Oh, okay, moo. A what of sheep? A flock of sheep. A what of fish? School of fish. A what of cells? A battery of cells. Okay. When we're talking about not body cells, okay, but electrical cells, a battery of cells. That's where the word battery comes from. Now, if we draw one cell. No, let's not draw it like that. We normally don't have cells lying on their side. Let's draw a typical Duracell. (1,5 volts). There you are. Can anyone tell me which part of that cell is the positive terminal? So how would I draw the symbol for that cell? Long one and then the short one. Vertically. They are vertical. Horizontal. So you're saying that cell should be represented other way around. Okay, we're getting there. Is that correct? It's 80% correct. No. Short one at the bottom. No, don't have to put the voltage sign there. The short one should be thicker. Should be thicker. Okay. That's the correct way for drawing a cell. A thin long line and a short thick line. The thin long line represents the positive terminal. The short thick line, the bottom of the cell usually, which is the negative terminal. Right, yes? No idea. Don't forget, your first cells that were made didn't look like that. They looked more like your 9-volt cells. Okay? And your 9-volt cell, what does that look like? Your 2 terminals at the top. One of them is positive, one of them is negative. That's your 9-volt cell. How would you draw that? Okay, that's how you would draw it. Right. So, okay. Now, if I took 3 cells and I connected them in series, what would it look like in real life? We all know what 3 cells in series with symbols look like. But what would it look like if I did this? Now, I'm not going to draw the short cell thicker, or short line thicker, because that's a pain in the butt. Okay? You know what it's meant to be. How would that look in real life? Would they be standing on top of each other like in a torch? Would they be lying next to each other? Like this. Like this. Where's the positive terminal on this one? Left or right? There. Okay, and the next one would be like that. And the next one, same situation. Okay, 1,5 volts, 1,5 volts, 1,5 volts. You all happy? So this is in series. Could anyone tell me what the total voltage of that battery of 3 cells is? Your total EMF, V total, is equal to 1.5 plus 1.5 plus 1.5 equals 4,5 volts. All happy with that? Okay, good. Can I do that? I can. I just have. How would I change that? The right-hand cell, I would have to reverse. Okay? Does it affect things? Serious? What would the voltage of that battery of cells now be? Nothing flows. No, it would flow. Let's just have a look. You say 1.5 volts. This cell over here is pushing electricity which way? Always think of conventional. Okay, so that way, you agree. And this one? And this one? You agree that these two cancel each other out. And I'm left with 1,5 volts. Do you agree it's stupid? No one should do that. Okay? Because rather just take 2 cells out of your battery than turn one around. Okay, so you turn 2 cells around, they fight against each other, they neutralize each other, you're left with only one. Okay, what would happen if I turn 2 cells around? So I'd have 2 in that direction, 1 in that direction. What would that boil down to? 1.5 in that direction. Okay. Electricity grade 11s is simple stuff. It's not difficult. Tomorrow we look at parallel cells. Okay? Thank you.